Hi everyone, we are the group 19 from the ESS 523, and our final project focus on the particle-Kalman filter for the Bipedal LiDAR-based slam. So imagine a walking blindfold through a hospital, no GPS, shiny floors that can sleep, and people moving around you. Yeah, you must know where you are and to centimeter and just build a map on the fly. And that's the everyday reality for autonomous Bipedal robot. And for such a Bipedal slam, the key challenges for the slam problem is the first is the nonlinear and discontinuous motion. And with every footstep, the robot base frame teleports related to the ground, and the simple linear models don't ever hold. And the second key challenge is the sensing in GPS is denied in certain spaces. The indoor settings like block GNSS, and we can only rely on LiDAR, depth cameras, and IMU and other joint encoders. And the third challenge would be the tight resources envelope. And a bit cannot log a 300-watt GPU, and the CPU budget and battery are very precious. So the slam must finish in a few milliseconds per update on embedded ARM or very low power x86 CPU. And the four success criteria for a pivotal slam is to achieve accuracy, consistency, the real time, and the scalability. The existing works of classic filters include the EKF and PF slam. For EKF, it's very fast, and the time for update is linear in the number of landmarks square. And however, it's rely on the first order linearization, and in our high step curvature gates, the approximation drifts, so it's not always holds. And for particle filter, it samples the whole posterior, and it can handle multimodal uncertainty and gross non-linearity. But however, it's needs dozens hundreds of particles each with its own map, and the runtime and memory scale like O(n) times n, and which is very costly with the memory and runtime. So here's our problem statement. Uh, Given the XK, which is six DOF-based poles in SE3, and N is the static landmark map, and the motion model PXK given like XK minus one UK and other things come from the IMU and encoders, and the sensor model PZK given XK and is obtained from LiDAR returns. Why is this object so hard? The joint posterior, you can see, is very high dimensional and non-Gaussian, and it's exactly inference is very intractable. And so that's it.
Our method leverages LiPo, advantage LiDAR, IMU, and kinematic integrations framework, which helps improve state estimations and mapping in complex environments. By using particle filter for pose estimation, we can track the robot's primary pose, X, Y, and yaw using LiDAR and IMU data. While an extended Kalman filter maintains a global map with shared landmarks, this separate the pose estimation and map maintenance help to reduce computational complexity. Our key advantage of our approach is the balance it achieves between accuracy and computational efficiency. Particle filters provide robust post estimation, especially in nonlinear scenarios, while EKFs efficiently updates the global map while with LiDAR data. As for resampling step in particle filter, it ensures that only high quality particles are kept and avoiding the degradacy issue that can occur when particle loss their relevance. As shown in the system architecture slides, our data flow is straightforward. IMU and LiDAR data are used in particle filter for tracking robot pose, while EKF performance map updating based on particle pose and other data. Finally, the resampling date ensures that the particle set remains optimal. This hybrid approach provides an effective methods for real-time localization and mapping in dynamic and cluttering environments, ensuring accuracy and efficiency even the limited computational resource of mobile robotics.
Here are some of our preliminary results. The top row are baseline measurements and mapping that are done by the EVCO algorithm, which our approach is based on. And on the second row are some of our preliminary maps and preliminary pose estimations where we leverage our coupled PF and LiCo approach. As you can see, due to the problem space in our implementation, we are only able to obtain a very limited map as well as an incomplete path estimation, but um, it is still apparent that our approach shows promise in both the positional estimation and mapping aspects. In conclusion of the whole presentation, we some more things that can be done with our project is further system integration in order to improve usability and positional accuracy. Some of the limitations of this project so far is that we face significant challenges in the integration of the particle filtering with the existing EKF-based system that prevented us from fully implementing and fixing the particle filtering system. Moreover, particle filters inherently necessitate more computing resources compared to an EKF, which may limit the actual rollout of our filter. So further works can be an incorporation of directional endpoint features in order to improve estimation, especially in indoor or smooth environments where it is difficult for LiDAR to extract useful features, as well as further testing of the whole system with more varied and robust environments. Okay. Thank you so much for listening, and I hope our presentation was useful.